Welcome to This Explainer. Okay, today we are doing something I am absolutely pumped about. We are finally breaking open the black box of the digital devices we literally rely on every single day. Think about it. You stare at screens, you tap on glass, and you trust invisible networks with your most private data. But what is actually going on under the hood?
I mean, really, how does a basic piece of silicon actually think? It's kind of fascinating when you stop and consider it. How does a lifeless piece of metal, some plastic, and a bunch of refined sand somehow process our entire digital world? It feels like magic, right? Well, actually, it's just incredibly well-organized logic.
All right, let's dive into this. Section 1, the core of computing. We're looking at the IPO model and beyond. So, before we even touch the sci-fi stuff like AI or quantum realms, we've got to acknowledge the fundamental heartbeat of literally every computing device out there: the input, process, output, or IPO model. Data enters, specific instructions manipulate it, and meaningful results get returned to you. It's an elegantly simple loop, but it totally drives our entire digital infrastructure.
Now, driving that IPO loop is the ultimate symbiotic relationship. On one side, we have hardware, the physical processors, the memory, the tangible stuff you can actually hold in your hand. On the other side, software, the intangible logic and data. Look, without software, your computer is basically just a really expensive paperweight. But without the hardware, all that brilliant logic has absolutely nowhere to execute.
And if you peel back the layers, at the foundational logic level, all this software just boils down to binary. Computers operate on a base 2 system because electronic components are flawlessly good at holding two distinct states, like a voltage being high or low, on or off. The real mind blower here is that every single high-res photo you take, every encrypted text, every movie you stream, is ultimately just a massively intricate, infinitely stacked pile of those fundamental ones and zeros.
But processing billions of ones and zeros requires a killer blueprint. Enter the von Neumann architecture model. Proposed by John von Neumann way back in 1945, this was the absolute breakthrough that birthed modern computing. See, instead of building separate physical hardware systems for instructions and then another for data, he realized you could just store both programs and data in the exact same memory space. It was a total game changer for flexible programming.
Moving right along to Section 2, Evolution. We are going from giant vacuum tubes all the way to AI.
So, computing history is usually sliced up into 5 distinct generations. We kick off in the 1940s and 50s with vacuum tubes, upgrade to transistors in the 50s and 60s, and then hit integrated circuits in the 60s and 70s. The 70s brought us the microprocessors that we're basically still using today, and now we are standing right on the edge of the 5th generation, artificial intelligence and quantum computing. And as you'll see, with every single chronological leap, these systems got drastically smaller, insanely faster, and way more accessible to everyday people.
Seriously, the sheer physical scale of early computing is just wild when you compare it to the phone in your pocket. First-generation behemoths like the ENIAC literally filled entire rooms. They generated massive amounts of heat, and honestly, they broke down constantly because those vacuum tubes kept blowing out like fragile, cheap light bulbs. All of that just to do basic calculations that a modern digital watch crushes in a millisecond today.
Which brings us perfectly to Section 3, Performance and Moore's Law. Let's see how things got so small.
So, the real secret to shrinking room-sized calculators down into pocket-sized supercomputers comes from a famous observation in 1965 by Intel co-founder Gordon Moore. He noticed that the number of transistors you could fit onto an integrated circuit was doubling roughly every 2 years, which effectively chopped the cost in half. This exponential growth curve, known as Moore's Law, has pretty much dictated the tech industry's entire roadmap for decades.
To put that kind of crazy exponential growth into perspective, just look at this number: 10 billion. That is roughly the number of microscopic transistors that tech companies can pack onto a typical modern microprocessor right now. 10 billion. Now, sure, we are rapidly hitting the absolute physical limits of silicon miniaturization. You can only shrink an atom so much. But this relentless, decades-long drive to pack more processing power into tiny spaces, that is what fundamentally built our modern world.
Let's zoom out a bit for Section 4, the modern computer ecosystem. We're looking at everything from desktops to the Internet of Things.
And this brilliantly illustrates how, in modern computing, form absolutely follows function.
On one end of the spectrum, traditional desktop setups give power users incredible, highly customizable performance and superior cooling, but obviously you sacrifice mobility. On the other end, we've got modern 2-in-1 hybrid laptops. You trade a little bit of that raw power for thermal efficiency, giving you an ultra-portable reality that seamlessly adapts to how we actually live and work on the go.
But honestly, we really need to expand our definition of what a computer actually is today. We are now firmly living in the era of embedded systems and the Internet of Things, or IoT. A modern household is a seamlessly connected web. Everything from your thermostat to your refrigerator, your washing machine, even your light bulbs, they all have specialized mini computers baked inside. They've got built-in sensors, they hop on your Wi-Fi, and they are constantly processing data to automate your daily life.
All right, the final piece of the puzzle, Section 5, Networking and Security Basics, Connecting the World.
Let's demystify the cloud for a second. Spoiler alert, the cloud is simply someone else's server sitting in a massive data center somewhere. When you do something as simple as sending an email, your data takes a very real, very physical path. It flows from the global internet, blasts through security firewalls, gets routed around by routers, moves through local access switches, and finally beams out of a Wi-Fi point straight to your laptop. It is a highly complex logistical highway, and it's happening in the blink of an eye.
So why this matters to you specifically is because that constant global connection completely exposes your personal data to the world. And that's exactly where the CIA triad of security comes in. We're talking confidentiality, integrity, and availability. This right here is the gold standard for information security. It ensures your data stays private from snooping eyes, remains completely accurate and untampered with, and is actually there for you when you need to access it. Understanding and using this triad is how cybersecurity protects your digital life from everyday threats like malware, phishing scams, and denial of service attacks.
We have honestly come such an incredibly long way from those room-sized, heat-cranking vacuum tubes of the 1940s, haven't we? Now we've got billions of connected transistors powering global networks right in our pockets. But this evolution is far from over. As artificial intelligence and quantum physics start merging with our daily devices, what do you think the next generation of the black box is going to look like for you? Will our physical reality just seamlessly integrate with all this computational power? It is a thrilling prospect, and I really hope this explainer gave you the foundational knowledge you need to grasp whatever incredible tech comes next.